All right, let's dive into an idea that is, well, it's pretty wild. What if the fundamental building blocks of our universe aren't little points, but are actual physical knots? And what if that spooky action at a distance, quantum entanglement, isn't spooky at all, but a real braid woven right into the fabric of reality itself?
So let's just start with that big question, right? For a second, forget all the complicated math. Just try to picture it. Two particles connected across maybe millions of miles, not through some mystical force, but because they are literally physically tied together, like two threads in some kind of grand cosmic tapestry. That's the core idea we're going to explore today. So here's our roadmap. First, we'll look at the whole new fabric of reality this theory proposes. Then we'll see how particles get reimagined as knots and entanglement as a braid. After that, we're going to get into the really crucial part, the actual testable predictions. And finally, we'll wrap up with some seriously mind-bending consequences that stretch all the way from the cosmos down to pure mathematics. Okay, first up, a new fabric of reality. See, to really get this theory, you kind of have to throw out our everyday idea of space as this smooth, empty, continuous thing. We need to start picturing something with a bit more texture.
This is the stochastic background field theory, or SBF for short. The big idea here is that at the absolute tiniest level, reality isn't smooth at all. It's a network, a grid of tiny, distinct grains. Think of it like the pixels on your screen. In this model, space and time aren't the fundamental stage where everything happens. No, they're what emerge from the interactions between all these little pixels. So, if reality is a kind of fabric, then what are the particles? What's an electron really? Well, that brings us to the next big idea, and it's where the theory really gets its name: particles as knots. This theory proposes a whole new physical alphabet for particles. An electron isn't just a point of charge anymore. It's a simple trefoil knot. That's the most basic knot you can make. A heavier particle, like a muon, is a more complex cinquefoil knot. And a tau particle, an even more complex stevedore knot. All of a sudden, a particle's properties, like its mass, are directly tied to the complexity of its physical knot. And this is how the SBF theory tries to explain all those weird quantum properties. Take spin, that famously bizarre quantum number. Well, it's not so abstract anymore. In this model, spin is simply the physical twist stored in the knot. A particle with spin is literally a twisted piece of the fabric of space-time. All right. So, we've got individual knots acting as particles. Makes sense. But what happens when they interact? This is where we get to the real heart of the whole theory: entanglement as a braid. This quote from the source material it nails it perfectly. When two particles, say two electrons, become entangled, their individual knots are literally braided together. They form one single composite structure with a shared twist. They're not two separate things communicating anymore. They're one single topological object. And get this, it gets incredibly specific. The different quantum states we talk about in physics aren't just abstract labels anymore. They correspond to actual physical braid configurations. One state is a right-handed double helix, another is a left-handed one, and a third is this symmetric figure eight. All of that abstract quantum mechanics suddenly has a real, physical shape you can almost picture. So, what about that spooky action at a distance? How does this model solve it? Well, the theory says these braided particles share what's called a time vector. Just think of it like this. Because they're one single object, they step through that granular network of reality together in perfect lockstep. A change to one end of the braid is instantly, and I mean instantly, felt at the other end, because the whole thing is updating as one unified structure. Now, this is all a really beautiful, elegant idea. But is it science? Well, for a theory to be science, it needs to make predictions we can actually go out and test. And that brings us to our next section: predictions from the weave. And here's the bottom line, right? A cool story isn't enough in physics. For a theory to be taken seriously, it has to make real, falsifiable predictions. It has to spit out hard numbers that scientists can actually measure in an experiment, and maybe even prove wrong. And SBF theory delivers. Its first major prediction is about the energy cost of creating an entangled state. Tying that braid should take a very specific amount of energy. The theory calculates that cost to be exactly this: 1.42 times 10 to the minus 5 electron volts. Now that is a number we can hunt for. So how does that number stack up against reality? Well, this chart compares it to a known experimental value from a system called positronium. Now, it's not a perfect match, you can see that, but it's in the same ballpark. It's the same order of magnitude. And let me tell you, in theoretical physics, getting that close on a first pass, that's a very encouraging sign that you might be on the right track.
The theory also predicts how fragile these braids are. At room temperature, the thermal vibrations of the universe will eventually shake them apart. SBF calculates this decoherence time to be about 10 to the minus 7 seconds. Again, another hard number that experimentalists can go out and try to measure.
So, the theory has some testable legs to stand on. But if it's right, what does it really mean for the big picture? That's our final section. And honestly, this is where things get truly wild. Cosmic and classic consequences. Okay, this is where you might need to sit down for a second. If entanglement is a real, physical braid made of energy, then good old E equals mc squared tells us it should have mass. And if it has mass, it should have a tiny but measurable gravitational footprint. And once again, the theory gives us a number to shoot for. Let's say you entangle two particles between two satellites 1,000 kilometers apart. That connecting braid would have a mass, an effective mass, of about 10 to the minus 18 kilograms. That's almost nothing, but crucially, it's not zero. It might just be detectable, giving us a way to actually weigh a quantum connection. But the implications of a granular universe don't stop out in space. They might just reach into the ivory tower of pure mathematics. In fact, one of the most incredible claims of SBF theory is that it offers a physical solution to one of the famous Millennium Prize problems. The problem is all about the equations that describe how fluids flow and whether they can break down and lead to singularities, points where things like velocity become infinite. SBF theory comes along and completely reframes the question. It says, hold on, this isn't a pure math problem, it's a physics problem. The math is only so hard because it's based on a flawed assumption that space is smooth and continuous. And here's the punchline. In a granular pixelated universe, you just can't have a singularity. It's physically impossible. You can't have infinite velocity when your universe is built from finite little pixels and has an absolute maximum speed limit, the speed of light. That dreaded singularity, it turns out, might just be a mathematical ghost that only appears because our old models forgot that the universe has a fundamental graininess. And that leaves us with this one final, really tantalizing thought. The SBF theory paints a picture of a universe that is a grand, intricate tapestry. Particles are the knots, entanglement is the braid, and the laws of physics are just the rules of the weave. If this vision of reality is even close to being right, it makes you wonder, doesn't it? What other profound secrets are just waiting to be untangled?